As I said before, I travel a lot, I go around the world, and then I was in Munich and I found a really, really interesting company coming all the way from Long Island in New York, PLX. Itai is here to tell us how he can actually integrate any kind of photonic device in a complete new way, new fashion for harsh environments. Thank you very much for being with us. The floor is yours.
Thank you, Jose, for the introduction. Good afternoon. As Jose said, PLX is located in Long Island, New York. PLX is a technology company. In simplicity, we specialize in bending, folding, transmitting light with high accuracy in harsh environment. We also known as the pioneer of the hollow retroreflector. For some of you who don't know what is a retroreflector, I think this is kind of a cool presentation. Retroreflector is almost like the invariable mirror. I think that the image, I don't know which one works, sorry. Top one. Okay. This one is not an invariable mirror. You can see the beam wandering all around. This is the retroreflector function. Essentially transmit the beam back to the source with very high accuracy. So we're talking about space applications that becomes very, very significant. We're talking about sub-second accuracies. You can see in the one on the left, the effect. You can see the flashlight that essentially stays right on spot. How do you introduce the technology in kind of five minutes? That's kind of complicated, so I think that this video hopefully will make it a bit simpler. The next slide would be the video. The technology is comprised, or the technology that I want to introduce today is the monolithic optical structure technology, comprised of monolithic structures, invariant optics. This is the core of the technology, incorporates hollow retroreflector and lightweight optics. Lightweight optics becomes very significant in space. This is all integrates into multiple systems. The music is just for fun, but I think that the video itself will kind of try to explain. What we see here is a typical lab setup for the people that are actually in the spectroscopy industry. You might recognize this structure. The idea behind this technology is that you can take multiple optical components. It doesn't have to be plano optics. It can be freeform optics. It can be conventional optics. As long as we match the material with CTE comparable using that technology, which for obvious reason I'm not explaining exactly how it's being done, but the sandwich-like structure that you see here is a simplification of a steel interferometer, which is a form of Michelson interferometer. With the retroreflector, this becomes completely invariant. The emphasis is on athermal design. This is a very similar setup that you saw before on that video. Again, multiple optical elements, putting them into a sandwich-like structure, making it rugged, optically stable, mechanically stable, mounting it with some exotic materials, and that is actually where I would need some help. As a technology company, we do invest a lot in research and design. New materials is always something that is desirable. We do work with multiple materials, including beryllium for space. And the 4 blocks that I showed before. We talked about the monolithic optical assemblies, which I showed you before in the video. The invariant optics is here an example of a retroreflector and how it can be translated laterally. This doesn't work. This is a segment of a roof mirror, and this is a flat mirror, which can be also a beam splitter. And someone mentioned before, earlier, I think it was from KLabs, the free space optics. This, for example, this configuration designed for space with high accuracies can be actually very, very significant in triangulation and additional communication between satellites, kind of saving some energy. This is some of the application that we can find our technology. Laser trackers, cavities, laser cavities, bore sighting and spectroscopy are technologies that you see our instrument. The LiDAR and free space optics indeed are the emerging one. These are the industries that we serve. Some of the companies that we provide our instrumentation and assemblies. For the aerospace system integration, we do have multiple projects. I just brought some few examples. This is something you can look at later. Several space programs we participated. The heritage goes back to 1975. This was with the Apollo-Soyuz. This particular project was for the tropospheric emission spectrometer. This was in service for 14 years. This was an interferometer that we built together with JPL. All was done with multiple optical assemblies made from beryllium. This one in particular was a project that's still running by ESA. This is a V-shape interferometer. This is for the ExoMars, monitoring the Mars atmosphere. This is the V-shape, one retroreflector here, the other retroreflector is on the other side. For NASA, and a very interesting project which is related to the next slide that I'll show you. This is bore sighting in space or alignment in space. The short video will explain it.
Once the Atlas instrument transmits 6 laser beams to Earth, the telescope receives the photons that bounce back from Earth.
Hey there, I'm Tyler Evans, an optomechanical engineer on the ISAT-2 mission, working on the Atlas instrument. So for the receiver subsystem, the biggest component is the telescope, which is 0.8 meters in diameter, which is about 31.5 inches in diameter for the primary dish. So the primary dish is the reflective surface that you see, which has curvature to it. And the way that it works is light goes into the primary dish and is collected by this big dish, and it gets focused up into the secondary mirror, which is at the end of this tower. And then the secondary mirror shines the light and focuses it down through that tube to the center, to the back of the telescope where the detectors are. And this telescope is made out of beryllium, which is kind of a unique material that has a high strength to weight ratio. So this whole telescope only weighs 50 pounds. Now, to know which way the telescope is pointing, there's 4 green lasers that are coming out of the telescope. So if you look into the main dish, you can see the 4 TAMS spots, the Telescope Alignment Monitoring System. And those go out of the telescope and get picked off by this periscope. And the receiver periscope picks up the light from the telescope and bends it back into the LRS. The LRS is the Laser Reference System camera. So that's really the brains behind the closed loop control system that looks at those 4 spots and knows, as it tracks those 4 spots, how the telescope is pointing.
The next slide, which is somewhat related, this is a completely different application, military application, but this is what we contribute to the aerospace industry as well as the defense industry. Bore sighting between multiple elements. This is bore sighting of 2 cameras, infrared and visible, as well as the alignment mechanism and the telescope. All of that needs to be withstanding harsh environments. So we're talking about high shock, vibration, and maintaining very high accuracies, such as quarter arc second. Because our optics is hollow, we benefit from the full spectral. In terms of size, this is an example of things we've done in the past. Multiple projects that we worked on. This is actually a spectrometer for the gas industry. These are the components that you saw before, the assemblies that you've seen before, at least one of them in the Atlas program. And for the LiDAR system, this is a simplification of an optical setup. This is again an example of an interferometer, but LiDAR can be made with this particular technology. Free space optics with modulator, without modulator. So we deal with different materials. This particular retroreflector is comprised of 3 silicon mirrors. 2 of them are regular silicon wafers. The third one is MEMS, made by Boston Micromachining. We created that retroreflector, which is very instrumental in low voltage environment for either space communication and communication in general. And what I've mentioned before, the lateral transfer hollow retroreflector can be very much instrumental if we want to have communication between satellite or communication between ground and satellite. It can be lateral transfer hollow retroreflector. It can be a LiDAR system. Multiple applications. And thank you.